This lesson is going to cover the basics of logarithms. So this is just an introduction. So we're going to talk about what a logarithm is and how it's related to the exponential function. And you can see in the objective, it's talking about how logarithms and exponential functions are somehow inverses of each other. So with that said, let's go ahead and take a quick look back at some things that we already know in terms of inverses. So for a practice problem here, it says write the inverse of each of the following functions and analytically verify that they are inverses. So remember, to find the inverse of a function, to write the inverse function, the idea is that the inverse function replaces the x with the y and vice versa. So the x becomes the y and the y becomes the x. So here it says f of x, so we can replace that with y. So it'll say, that is y, and then we're going to replace it with x. So it'll say x equals 2/3 times y minus 7, and then we're going to isolate y in that case. So we'd have to add 7 to both sides and then multiply by 3 over 2. Ultimately, you would get the inverse of f of x is equal to 3 over 2x plus 21 over 2. I'm not going to get into the long detailed work of that. We've had plenty of practice with writing inverse functions. But then the second part of this, it says, and analytically verify that they are inverses. Remember, to show analytically that two functions are inverses of each other, what you do is you plug one of the functions into the x of the other function. So we could say that the inverse of f of x, so that would mean, in this case, we are plugging the f function into the inverse function. So we're plugging the 2/3 x minus 7 into this x value here, and that's what we get here. We get 3 over 2 times 2/3 x minus 7 in parentheses, and then plus 21 over 2. Remember, if these are actually inverse functions, then once this is all simplified, you should get x out as a result. Well, if we distribute the 3 halves to the inside of that, we end up with x minus 21 over 2, and then the plus 21 over 2 out back, and those cancel out, so you're just left with the inverse of f of x is x. And that's what verifies that they are inverses. If the inverse of the function, or inverse f of f equals x, then you know they're inverses. For number 2, this is a radical function, so we know that the inverse of this should be a parabola. We would say, we would replace this y value with x and this x value with y. We would add 3 to both sides, then divide by 5, then square both sides, then subtract 1, then divide by 2. It's a bit of a long process, but your end result should be, if you were to expand everything out, should be 1 over 50 x squared plus 3 over 25x minus 8 over 25. And I'm not going to get into the big long work of that, but that is your answer. You should maybe work through that and verify that that is correct, just for your own understanding. But with that said, let's go on to a little bit more difficult problem. How do we write an inverse of a parabola where the a value is not 1? Well, remember, the first thing we have to do is we have to replace the x and y values, swap them out. So instead of y, we're going to put x, and instead of x, we're going to put y. But you notice on the right-hand side here, we have two y values. We have a y squared and a y. So the goal is to get y by itself. There is only one method that allows us to get y by itself when we have a quadratic written like this, and that is by completing the square. So remember, to complete the square, you have to figure out what it is that we are squaring, and therefore what we have to add on both sides of this equation. So the first thing I'm going to do to clean this up is I'm going to factor out a 3 from both of the y terms, because I can see that they both have a 3 factored out of it. So we get 3 times the quantity y squared minus 10y, and then this plus 82 is out back later on. We'll deal with that later. But now, because the a value on the y squared is 1, we can actually complete the square on this thing inside. Y squared minus 10y, the completed square would be y minus 5 squared. Remember, you take the b value and divide it by 2, and that gives you your completed square. But remember, when we do that, if we were to expand this and say y minus 5 squared, that would be y minus 5 times y minus 5. You're not going to get y squared minus 10y. You're going to get y squared minus 10y plus 25 because you got to distribute all of that out. Well, let me take a step back there. So if I expand all that out, notice there's a plus 25 here that wasn't here before. And in fact, there's even more there because that 25 would have been distributed by the 3. So in all reality, what we did here is we added 75 to our original equation, and we didn't want to add 75 to our original equation. That changes the value. So if we added 75 to this equation, if we can subtract 75, that will balance it out. So I added 25 inside the parentheses, which means I added 75 after I distribute. So to cancel out that adding of 75 that wasn't up there to start with, I'm going to subtract 75 to zero that out. Well, 82 minus 75 is in fact 7. Now, before we go any further, we should expand this out, multiply it out, multiply the 3 out, add the 7, and when we do that, we would get what we originally started with of 3y squared minus 30y plus 82. Now, from here, we need to isolate y. So the first thing we need to get rid of is the things outside the parentheses. Well, think of your order of operations, but going backwards. So here, the first thing we would do after we plug in a y is subtract the 5, then we would square, then we would multiply by 3, then we would add 7. So if we're going to undo that, we're going to do everything in backwards order. So we're going to subtract 7 from both sides. So we get x minus 7 on the other side. We're going to divide both sides by 3, so we end up with 1/3 times x minus 7. And then we're going to square root both sides. And we could get the plus or the minus. That all depends on which part of the parabola we want if we're graphing this. And we're going to add 5 to both sides. And there we get our radical function. Now, that is our inverse function. So we say the inverse of g is equal to radical 1/3 times x minus 7 plus 5. Now, to verify this, remember, we're going to take either this original g of x and plug it into x down here, or we're going to take this and plug it into the x's up here. Either way will work. In my case, I took g of x up here and I plugged it into the x there. The reason I did that is because there's only one x to plug in down here. If I were to do it the other way and plug this in up here, I'd have 2 x's to plug into. So I just decided to try and take it the easier way. Now notice in this case, when I plug that in, I can simplify that 82 minus 7. That becomes 75, right? And then I can distribute that 1/3 in there. Distribute the 1/3, so that becomes x squared. This becomes negative 10x, and then this 75, 1/3 of that became 25. And then I notice what's inside the radical is actually a perfect square. So I could write the x squared minus 10x plus 25 as x minus 5 squared. And then as a result of that, we can see the radical and the square cancel each other out. And so we're left with x minus 5 plus 5. And then x minus 5 plus 5 is just x. And therefore, we have just verified that the function that I ended with is actually the inverse of the function I started with. So that's kind of cool. That's just a quick review, maybe a little bit more difficult problems than we've seen in the past, but that should warm us up to the idea of where we're going with this. Now remember an inverse operation. Inverse operations are operations that undo one another. They are opposites to one another. So we can say that addition and subtraction are inverse operations. So here's an example of that. If I have 7 equals x plus 5, well, how do I get the x by itself? I'm going to subtract 5. Why? Because your teacher told you? No, because we were adding 5 to x, and so to get rid of adding by 5, we are going to subtract 5 because those are inverse operations. Now, obviously, we're going to get 2 out of that. Some other inverse operations, multiplication and division, are inverse operations. We know this. This is something that we've learned a long time ago. But if I have 8 equals x divided by 2, To get x by itself, I'm going to do the opposite of dividing by 2, and which is to multiply both sides by 2. So we end up with 16 equals x. Multiplication and division are inverse operations. Well, here's another one. What is the inverse of squaring something? Well, we know that. The inverse of squaring something is square rooting something. That's why a parabola, which is a function which is x squared, its inverse is the radical x. They are inverse operations. Now, checking this out, if I have 25 equals x squared, how do I get x by itself? Well, I square root, because x squared, squaring, and square rooting are inverse operations. So in this case, we get plus or minus 5. Another look at this is if I had 9 equals radical x. Well, how do I get x by itself? I need to get rid of the radical. How do I get rid of the radical? I do the opposite of doing the radical. I take the square of both sides. So be careful when you're using your language. I know a lot of you will use these interchangeably. They're not. They're completely opposites to each other. I see a lot of people saying, oh, well, look, what is that? That's squaring. No, it's not. It's square rooting, right? How do I get rid of square rooting? Well, you square root it. No, you square it. You square a square root to get rid of it, right? And so you're left with x equals 81. So that's squaring and square rooting. Well, here, what about trig functions? The inverse of a trig function is an arctrig function. That's something that we learned at the beginning of this year. So if I have a function or an equation that says 0.5 equals sine of x, how can I get x by itself? What is it that I need to get rid of to get x by itself? And the answer is we need to get rid of that sine function. How do I get rid of sine? Well, I take the arc sine of both sides, because sine and arc sine are inverse operations. And so inverse operations cancel each other out, and that's why you're left with x. Oh, this is all making sense. It all goes together. That's why they're inverse operations. Anyways, just going back to this, the arc sine of 0.5 is 30 degrees, and if we convert that to radians, we get pi over 6. In fact, we can see our special right triangles there of 30, 60, 90. Not going to get into that right now, but it's kind of a cool connection. Here's the next one. You guys learn in Math 1 an exponent. What an exponential function looks like, what it does. We've done a little bit of it here this year. But what is the inverse of exponents? Well, you see it on the screen. It says exponents and logarithms are inverse operations. And that is true. But if I had an equation that said 16 equals 2 to the x, I can figure out x on my own. This is a nice clean whole number. 2, 4, 8, 16. X would be 4. 2 to the 4th is 16. But if this didn't say 16, if it said like 12, or if it said 13, we would have a hard time figuring out what x is in just the manner of looking for a whole number exponent, because it wouldn't be a whole number. It would be a decimal value, or a non-whole number value at least. So how is it that I can get x by itself? That's the goal. What do I need to get rid of? I don't need to just get rid of the 2. I need to get rid of the idea of raising this exponent here. How do I get rid of exponents? And so that's what we're looking at today, and that's what's called a logarithm. A logarithm, okay? The inverse of an exponential function is a logarithm, okay? It undoes exponents, right? It undoes exponents when the exponent is a variable. Now notice, it's when the exponent is a variable. If the exponent were a number, so like if the equation, going back, let me go back real fast here. If the equation had an exponent in it, like this equation, let's see, like this equation did here, where it said 25 equals x squared, we can get rid of the exponent easily by taking the radical with the root index that matches that exponent, or we could raise it to the 1/2 power. But what we're talking about here with logarithms is we're saying that the exponent itself is the variable. It's not a number. What is the number? The base is the number. So when the base of the exponent, the base of an exponential expression is a number, and the exponent is the variable, then a logarithm is going to help us undo our exponent in order to get the variable by itself. So it isolates, like I said, it isolates the exponent. So here's what the rule says. This is the definition of logarithm, okay? Now we can develop all the rules that revolve around this, but this is just somebody saying, okay, I don't know necessarily how to undo this. I'm going to figure it out as time goes on. But for now, to undo an exponent, I'm going to call this log. I'm going to call this the logarithm. And here's what it looks like. If a is your base and b is your exponent, and the result of that is equal to c, then that's going to be equivalent to the log with a base or a subscript of a of c equals b. Now there's a pattern here that holds true in all logarithms, and it's very important that we grasp this pattern, because when we write logs from exponentials, it's going to be the same every single time. Notice when I write a log, there is a subscript. That subscript is always the base of the exponent. The base of the exponent is the base of the log, okay? So these two equations are equivalent in terms of the values that you get out, okay? So a is the base of the exponent. The exponent itself, the power, b, notice the exponent is here, and then the c is the result. So if you're looking at the exponential equation here, the a, if I'm rewriting it as a log, the base of the exponent goes in the subscript. The exponent itself is what the log is equal to, and then the answer to our exponential expression, c, is what's inside the log. In other words, this is the argument. The argument is c. Okay, so let's take a look at some examples of this so we know how to do this. Let's get some practice with this. Here we have an exponential expression, exponential equation that says 81 equals 3 to the x. Now I know we can solve for x. That's not the point right now. We can figure out what x is without the help of logarithms. But that's not the point. The point is to rewrite this in a logarithm form in such a way that gets x by itself. So remember, when we're doing this, we're taking the log, we're rewriting this as a log. The base of the log is always the base of the exponent, and what the log is equal to is x. So as a result of this, we get the log with a base of 3, we say, of 81 equals x. So we're just rearranging these numbers in a different order. So the base goes with the base of the log. That one's easy. And then these guys kind of swap. What the log is equal to, it's equal to the exponent. And then here, this number that the exponent was equal to is what's inside the log. So that's what we get for A. For B, same type of thing. What is the base? Well, the base is 3, so it's going to be log base 3. And then we're going to say of, we don't want to just put x there. We're not rewriting this exponent. I see a lot of students do this sometimes. They just say, oh, look, 3 to the x, so I'll just put 3 to the x. No, in fact, it's the exact opposite. It's 3 to the other thing. You put the other thing inside the log. So it's log base 3 of 72 equals x. Because remember, the log expression is always equal to the exponent over here. Now, in part C, there's an extra step that needs to be taken care of first. In order to get x by itself, we need to get the exponential expression by itself. So we need to get rid of this 19 first. So we're going to go ahead and add 19 to both sides first. And so we end up with 31. So we get 31 equals 5 to the x. Now, because we have the exponential expression now by itself, we can rewrite this using a log. It's going to be the log with a base of 5, right? Log with a base of 5 of, what's the argument going to be? The argument, the thing inside, is going to be the 31. And remember, the log expression is always equal to the exponent, and so your exponent is what it's equal to. So hopefully that gives you some foundation in terms of how to write a log. Why do we write it like this? Well, it's just terminology that mathematicians use in general to express isolating x. We're going to get more into why this works and how it works later on, but this is just the definition of a log. Let's go ahead and do some practice here. You've got 5 problems here, and the goal is to get x by itself by rewriting it as a logarithmic expression or equation. So go ahead and pause the video, do it yourself for a little while. Once you think you have some answers, push play and see how you did. For number 4, it says 12 equals 4 to the x. So when we do this, we're going to take the log. We're going to rewrite this as a log equation. So it'll say log with a base of 4, okay, of 12 equals x. Remember, it's always equal to the exponent. The base is always the subscript of the log, and then this guy is inside the log. For number 5, we can't get x by itself by taking the log first. We have to get rid of the plus 2 first. So we're going to subtract 2 from both sides. And so we end up with 40 equals 5 to the x. And then when I rewrite this as a logarithm, it'll say log base 5, and then of 40, and that's going to be equal to x. So just getting practice rewriting logs using the definition of a logarithm. Number 6, well, interestingly enough, number 6 we could write as a logarithm expression. We wouldn't need to, though. To get x by itself, we don't want to rewrite this as a log. In fact, let me go ahead and write it as a log so we can see what happens. It would be the log with a base of what? Well, it'd be the base of x. Because remember, the base of the function is always the base of the log. And that would be of 12, and then equals the exponent. In this case, the exponent is 3. So this equation is an absolutely true equation. The problem with this equation is that it didn't get x by itself. So we don't want to use that guy. That's not a good way to solve for x. This one's different. This is one we know how to do. How do we get x by itself? We got to ask ourselves, what is it that gets x by itself? Well, what is it that we need to get rid of? We need to get rid of that 3. Well, what is the operation on the 3? It's raising to the 3rd power. How do I get rid of raising to the 3rd power? I can either take the cube root, or I can raise it to the 1/3 power. So if I take the cube root or raise it to the 1/3 power, remember a power raised to a power you multiply. 3 times 1/3 is 1, so you're left with x to the 1st or just x. And so your answer could be written as x equals 12 to the 1/3 power. Again, you can write it as a logarithm, but that doesn't solve for x, and our goal here was to solve for x. All right, number 8 is kind of a fun one, because where is the variable? The variable is in the exponent. So we know that we're going to use a logarithm here. Well, let's see here. Would I get rid of this tangent first, or would I get rid of the base exponent first? And the answer is I would get rid of the 2 first. So the first step is to write this as a log. It'll say log, oh, sorry, I'm looking at number 8 here. Let's go back up to number 7. Let me skip back to that one. Well, again, I need to get the x by itself, so I need to solve for the exponent, so there will be a log. But I can't get there yet because I have a bunch of other stuff that has to be gotten rid of first. So I'm going to subtract by 4 on both sides. I get 95. I'm going to divide by 5 on both sides and get 19. Then I can use my logarithm expression because I only have an exponent left. So this will say log base 7 of what? Of 19 equals x plus 8. And then from here, to get x by itself, we're going to subtract 8 from both sides. Now notice, I want you to be very careful here. We are taking the log of 19. Okay, we're taking the log of 19. We cannot subtract 8 from the 19. The 19 is in parentheses essentially. So what we do is we put that negative 8 out front. We don't want to say log base 7 of 19 and then minus 8, because some people might confuse that and say, oh, it's 19 minus 8. No, it's not. It's the log of 19, whatever that is, minus 8. Okay? It's an order of operation thing. We need to make sure that we take the log of 19 before we subtract 8. not subtract 8 from 19 and then take the log. All right, back to number 8 now. Back to number 8. Well, we want to get rid of the 2 as the base, so we're going to write that as a log. That'll be log base 2 of 21 equals tangent of x. Okay, so that's just rewriting using logs. And then the next step to get x by itself is to get rid of the tangent. Well, how do I get rid of tangent? I take the arctangent. So if I take the arctangent of one side, I have to do it to the other. And then as a result of that, we get the arctangent of the log base 2 of 21 equals x. I know it looks kind of gross. It looks kind of like a disgusting equation. But the point is undoing a problem, just like solving for x in any linear function. What do we have to do first to get rid of the things that are keeping us from getting x by itself? So it's the same process, it's just adding more functions to the list. All right, let's go ahead and go on. Writing the inverse of an exponential function. So let's take a look at an example of this. Let's determine the inverse of each of these functions. Now, this is exactly the same as what we've been talking about with inverse functions all along. How do I write an inverse function? I write an inverse function by replacing the y with x and the x with y. So here it says f of x equals 9 to the x. So the first thing I'm going to do is going to swap those. So that's going to say x equals 9 to the y. Now the next step is to get y by itself. Because y is the exponent, the way we get y by itself is to take a log. So we say the log of base 9, log base 9 of x equals y. And there we have y by itself. Well, what do we call y? Y was the inverse of f. So we'd say the inverse of f of x is equal to log base 9 of x. Quick recap of that just to make sure we're good with this. We swapped out the x and the y's. And remember, our goal is to get y by itself. So we took the log we rewrote it as a log. And then because we have y equals, we've done our job. But what was the name of y? Y was the inverse of f. That's what we were looking for. All right, for option or for part D, how do we get x by itself? Well, this is a little bit backwards. This has a log in it. How do I get rid of a log? Well, the first thing we have to do is swap out our x and y's. So it's going to say x equals log base 5 of y. Well, how do I get rid of that log? Well, what's the opposite of log? The opposite of log is an exponential. So we're going to rewrite this in exponential form. So let's go back over here to this example here, right? We had the base of the exponent is 9. So the subscript of the log is 9, right? Okay, so what's the subscript of the log? It's 5. So what's the base of the exponent going to be? The base of the exponent is going to be 5. All right. Well, what happened over here? Well, where'd this x, the argument, the thing inside the x, is what the exponential expression was equal to. So the thing that's inside the log here, just like the x was inside the log here, the y is inside the log there. Right? So that is what the whole thing is going to be equal to. All right, the y, the thing the log was equal to was the exponent, right? So the thing that the log equals was the exponent. Well, what's the thing the log equals? The log equals x. So that means x is going to be our exponent, right? And then the argument is going to be what it's equal to. So we get 5 to the x equals y. We're just rewriting the log in exponential form now. So now I have y by itself. Well, what was y? Y was the inverse of g. So we'd say g inverse of x is 5 to the x. And that is our inverse function. All right. So let's take a look at some practice problems. You guys try these 3, see what you come up with. Pause the video and then come back and look at the answers to make sure you're good. So for h of x equals 12 to the x, we're looking for the inverse. So it's going to say x equals 12 to the y. We have to get y by itself, so we have to get rid of that exponent, or get rid of that 12. So we have to take the log, so it would be log base 12 of x equals y. And then we have y by itself, so it'll say the inverse of h is equal to log base 12 of x. Hopefully you got that one right. Number 10, Same thing, swap out your x's and y's. So this will say x equals 6 to the y minus 3 over 2. Now we have to get y by itself. Well, what's the first thing I need to get rid of? I need to get rid of that 2. So I'm going to multiply both sides by 2. I end up with 2x equals 6 to the y minus 3. Then the next thing I need to get rid of is a 3. So I'm going to add 3 to both sides. So I got 2x plus 3 equals 6 to the y. And now because y is the exponent, I have to do a logarithm. It's going to be log with a base 6, right? Because the base of the exponent is 6, log base 6 of, what's the argument? The argument is what it's equal to, of 2x plus 3. And then that's going to be equal to y. And as a result of that, we could say the inverse of f of x is equal to log base 6 of 2x plus 3. That was a little bit more difficult one there. For number 3, it's written as a log already. So we need to get rid of everything outside the log first. Actually, before we do that, let's swap out. Let's go ahead and do this one because this one's probably a little bit complicated. Let's go ahead and swap out the x's and the y's. So this will say x equals 7 times log base 4 of y minus 1. So that's what we did first. Okay. Then the next thing we have to do is get rid of that 7. So we're going to divide both sides by 7. So when you divide by 7, you get x over 7 equals log base 4 of y minus 1. Okay. Then the next step is to get rid of the log. Okay, so we have to rewrite this as an exponential. Well, what's the base on this? The base is, let me move these up here so I have a little bit more room. The base is 4, so it's going to be 4 raised to the x over 7. This is getting a little wonky, but that's okay. We deal with these kind of equations when we get to higher math. So x raised to the x over 7, 4 raised to the x over 7 equals y minus 1. And then from there, we'll add 1 to both sides. So you got 4 raised to the x over 7 plus 1 equals y. So there is our inverse, and now we just have to write it as an inverse function. So it's going to be inverse of g of x equals 4 to the x over 7 plus 1. So that wraps up this lesson. I know it was a little bit long-winded, but make sure you're taking good notes. If you have any questions for me, write them in the comments below or ask me by email, and I will see you again at a later time. Bye.